Welcome, everyone. Thank you for attending this webinar. I have people joining from Big Marker today and hopefully some people watching on YouTube as well. So we're going to talk about some of the big problems with big data when we're doing computation on a large amount of data and then managing the risk associated with this. So the subheading here is managing risks in AI. I think AI is used as a bit of a blanket statement there. So we're hopefully going to go beyond this as a buzzword and then really pick apart some concepts that are often misunderstood. So yeah, I encourage everyone to ask questions and I will save most of them till the end where we should have a bit more time for a kind of Q&A. Also, for those of you who have a license with us, you should be able to download the notebook and then have access to the kind of computation that I'm running as I'm doing this webinar. So let's have a look at the outline. We'll talk about some of the uses of machine learning and specifically how these uses are expressed in Wolfram language. We will go into bias and how bias is a necessary problem when it comes to working with data. We'll have a look at some specific examples of where bias has been an issue and some of the trade-offs you have to make. And then we'll go into validation of a model. Okay. How do you know a model works? You have to validate it before you can just trust it. We'll talk about making decisions as a human or as a computer, what the differences are, the explainability in our results, and then finally some ethical issues. But these issues will be kind of these components mentioned in the outline. I'll touch on them all as I go through. Okay, let's get started. So, what do we mean by artificial intelligence? And for the purposes of today's webinar, I'm going to say that there is no real intelligence going on there. In its current state, artificial intelligence is the automated creation of models that have some predictive power. Okay, some have better predictive power than others. Some have such great predictive power, it seems to mimic human behavior. And with that, I'm obviously referring to the latest large language models by OpenAI and DeepSeek and Anthropic, etc. Okay, so let's go straight into an example. I've got a collection of points here, and I am allowed to, with my own human intelligence, to move these points around and, decide where I think the line should be that goes through these points. Okay, so let's say I think this is a perfectly good fit using my own kind of human intelligence and human assumptions about the data, that kind of thing. Now, there always are assumptions that go into every model, especially this one. We can say that, I don't know, around here where there's not necessarily any data point, our past and future, or like in this case, to the left, to the right, experience of the data tells us something about the future behavior or the intermediate behavior. That's essentially what we're doing. So it's important to think about the assumptions we're making. When we do this kind of thing. Okay. I could even increase the degree of fit. So this is just a straight line. It has degree 1. You can see the actual um, parameters associated with this linear fit here, but I could maybe boost this up to 2 if I wanted a bit more of a different shape. But that's not the thing I'm trying to highlight here. If I click this automatic tab, I don't have to do anything. And what we have here is some Wolfram language function that is automating the fit of a linear curve, so a line, to these data points. Okay. It's automating the fit by optimizing these parameters of the model. Okay, so we've chosen a model that's a linear one, and then it's automatically optimized the parameters of that model. Okay, and you can think about this. It might be minimizing the residuals. Okay, the distance between the line and the individual data points. So you can see I was quite close with my human intelligence, but this is an instance where if you have the tools available, it makes sense to automate this process. And I'm talking about the process of optimizing parameters there. And maybe I should go into a little bit of the detail of what's going on with, artificial intelligence in that way. And that specific instance, let's say, of artificial intelligence is really just machine learning. So it requires the uh, the input that you're using. So this input can be any domain, but that input needs to be what's called vectorized, so encoded as a vector. Okay, and then this vector is passed through a series of layers in something that we might call a neural net. Okay, and then it's decoded again. So just as it was encoded, it's decoded to get back to the original domain of input, but this time it's the output because it's kind of passed through the model. Okay, and if we want our artificial intelligence to carry out some kind of prediction or classification or fit in this case, uh, then when I say the automated tuning of parameters, what I really mean is like the weights of the neural network. Okay, so they take the form of the parameters in that case. And this optimizing, if you're talking about neural nets, this happens when you train the model on training data. Okay, and we'll talk about the different types of learning a machine can do. Okay, but all this really is, if we want to look behind the scenes here, is a predefined kind of built-in Wolfram language function that's finding the best fit to these data points. Okay, the next section is when we should use machine learning. So a general rule is that when you are data rich and understanding poor, machine learning will help you. Okay. Uh, if your understanding is good already, then perhaps you can just use a model that is re- relied upon already, that is a well-known, established in the literature, etc. And then maybe you only have a couple of parameters to fit to that model. So with this, I want to give an example. Take ballistics, like the trajectory of some ball or a cannon or something like this. Okay, we know very well how ballistics behave. We know the differential equations that describe the movement. So maybe we can start with a kind of base uh, differential equation model, and maybe we have a parameter to fit that's like the drag coefficient of the medium it's in, or something like this. Okay, in that case, it's probably easier to start off with a classical model and then just fit the extra parameters. Okay, A lot of the time, we don't have this understanding, okay? So we need to essentially use our wealth of data to try to extract some understanding. And here are the basic paradigms under which that happens. We have supervised learning, where you have labeled data. So you have like labeled input to output examples, and training your model on these examples allow the model to, optimize its weights and internal parameters, that kind of thing, such that eventually, when it's had a lot of training data and it's ready to be tested, it might be able to generalize. Okay. Unsupervised learning is a bit different, where you don't necessarily have pairs of input to output. You just have the input, and in that sense, you're really training a model to identify differences between input. So it's like it might gain some conceptual understanding, or you'd hope so, that okay, this input looks a lot like this input, and it looks nothing like this other type of input. And then in the third case, we have reinforcement learning, which is not talked about as often in these webinars, and it's more associated with kind of self-driving machines like this, where depending on the performance of the automated thing, it gets a reward from its environment. So it knows to do less of a certain behavior or do more of another. Great. Okay. So hopefully that gave a useful catch up to those of you who maybe aren't as familiar with machine learning and wanted a quick introduction. So we've got a couple of examples of the uses of machine learning here, where the first one is a text classification. So I'm just going to start off very, very basic and just say this and see what we get. Because these are categories that ahead of time we've decided are important to try and classify. So it said the language is English. For some reason, it's got a Facebook topic. Now, this might be a bit of an outdated kind of category, uh, perhaps before my time even, but that's indeterminate. Sentiment is, I guess, positive, saying hello. It's not identified as spam. It's not found any profanity, uh, and name gender is irrelevant here. So let us try and kind of extract some to see how it performs. Have some more like intentional pieces of text. So how about say I went for a run. Okay, there's no need for you to see that. Okay, it seemed like we kind of got the same thing there. So let me try and add a bit more. There we go. So now I've kind of added some negative sentiment. I was hoping this would get a Facebook topic. Let me try. So now we've got the Facebook topic of fitness, but for some reason it's classed the sentiment as positive. So yeah, it's not. You can see how it's not always doing not always doing the right thing. How about this? I want to try and see if I can identify some spam. So let's say I kind of imitate a kind of spam email where I say like, you have won bill. Okay, so this one was identified as spam. So I probably spent a bit too long on that. You get the principle of text classification. Okay, the next one is image classification. where this time it's a nice way to see some of the functionality of Wolfram language as well. Because in order to do this, you have to essentially give access to an imaging device on your machine. So this could be your laptop webcam, it could be some external camera you've got connected. But if I can run $ imaging devices, and I've actually got these devices to choose from, and I've already set my default imaging device. So this is just to help the people watching. So I've got a couple of tabs here. At the moment, it's not, it's just waiting for an image. So I'm going to give it access to the current image. And you can see it's kind of real time identifying what's in that image. And thankfully, I'm identified as a person. Okay, now moving on to the facial gender, facial age. Okay, it's predicted I'm a bit older, but the camera quality isn't great. So, and then I can even ask it to classify facial expression here. So, yeah, if you have the notebook yourselves, you can have fun with this. Okay, so good insight into what kind of data we have and some of the built-in machine learning functions in Wolfram language. But now next, this one comes under prediction. So we're kind of estimating a value based on some information. And the example I've chosen for this is colorizing a grayscale image. So at the end of the day, this is making some prediction based on the grayscale values here. And it looks very reasonable that this black dog is on some green grass. Okay. What happens next? Okay. So this is, here we're going to get a language modeling neural net that's stored in this Wolfram neural net repository, which is part of the Wolfram ecosystem, where we store all of the like pre-trained neural nets that you can interact programmatically with. So this is a GPT trained on a corpus of book data. All right. So we've already downloaded this, and we're going to say she got out of the something and see what it comes out with. Okay, so it's come up with car. Um, I thought of a funny example earlier where perhaps could give it some Shakespeare. Mm, So that's pretty much what you'd expect from any book that includes the words "wherefore art." You'd probably follow it up with "thou." Okay, so there's sequence prediction, feature extraction. This is something that will come up a lot through this talk. So we've downloaded this net, which is it's a net of word vectors and the words it's got from Wikipedia. Okay, so this is that kind of vectorized data that I was talking about before. So we can have a look at the word king and see what it has for that word. So as I said, this is the vector representation of the word king. And let me just find the length of this. So we can see it's given us a list of lists, but I only want the inner list. So I'm going to just query it with the first part. So it has 100. Its length 100, right? Because this is a 100-dimensional word vector. So if you had 100 different coordinate axes, this would tell you where king is in that coordinate space. Okay. Now we're going to extract some more words and make an association between those words and their vectors. Okay. So this words to vectors thing, we can now query with more words and then actually find out which words are close to one another in a kind of feature space. So I'll just run this and then I can, um, yeah, we can discuss this a bit. So here we've used these vectors to navigate the feature space, finding words close to king and woman, but not so close to man. Okay, interesting. So we're not going to get the names of any kings there because we have to kind of distance ourselves from the word man. So there's a very interesting use of the whole concept of nearness. Okay, and I suppose what I want to say here is that it's very hard for humans to kind of picture things in this feature space, but it's quite easy for computers to do that because a computer will take something like an image and the features it extracts are not at all obvious to humans. Okay, and it's a good exercise. Like if you saw an image of a cat, you should ask yourselves like, what is it about this image that means I know it's a cat? And if you try and think of the reasons, like if it has pointy ears, you can always find a dog or some other creature that has pointy ears. So it's just that your brain kind of knows it is. Okay. Um, Somehow your brain just kind of figured that out, and there's not really a way right now that we can go inside the brain and find out what it's doing when it's doing this kind of classification. But you can go inside something like a neural net. And by the time you're quite deep into a neural net, it's very much not obvious what's going on. Okay. Yeah, there's no real way to kind of assign a human-like feature to the features that the computer is extracting at some level. Uh, if you're interested in this kind of thing, Stephen Wolfram's book, uh, "What is ChatGPT and what is it doing? How does it work and what is it doing?" is really good. Okay, it gives a great explanation of this kind of thing. Great. Okay, so if we can kind of see where things are in feature space, then we might actually use some other Wolfram language functions like feature space plot, feature space plot 3D. So these are really, really useful. Uh, this first example in the documentation is just the nearness of images of letters in the alphabet. Okay, so J and I are close. Uh, B and P are quite close. Y and V also. Okay, so you know I have a physics background, so it's quite straightforward for me to think about. Okay, once you vectorize something, of course, it makes sense to represent that vector in like a kind of coordinate space. Okay, and however many dimensions you have, you can always work out a kind of distance vector between one vector and another vector. Okay, if you want to actually visualize this on something like a feature space plot, you need to do some kind of dimension reduction on your, you know, on your data, let's say, because it's not very easy to imagine something that's 100 dimensional. Great. Okay, next one is synthesis, where I'm just going to show you something I kind of prepared earlier. We have some images that are corresponding to the styles of these artists, right? Da Vinci, Kandinsky, Monet, and Van Gogh. And this is something I prepared earlier. I used the built-in camera to just take an image of myself and it used this function image restyle of that image and then mapped it over these. So this is a kind of cool uh, cool use case of some of these built-in functions. It's quite a creative um, use case, I think. Right. Okay, now we can get into bias. So how can we manage bias? So it's important to first address that all data is biased in some way. Well, if we had no bias in our data whatsoever, then we would just be looking at random noise and we wouldn't really be able to infer anything from it other than the fact that it's random noise. Okay. And in this way, bias is useful. Okay. Um, in the previous examples, the only way we were able to classify, my facial gender or facial age is that these machine learning methods have been trained on data which is biased. Okay, it knows the difference between classes. Okay, so bias in data allows us to discriminate between different classes, and I mean discriminate in the purely technical way. There, not any kind of derogatory way. Okay, and then here I've just got some different types of bias. So if we just kind of blanket statement, dogs generally have bigger ears than cats, then um, okay, this might be a valid conclusion we can draw from data. This would be an example of good bias. Now, bad bias, on the other hand, we could have an unjustified amount of confidence in the data and the quality of our predictions. Okay, we might just kind of trust that our predictions are always going to be right. We might have insufficient data, and this is a trivial example of this. We might have bad data from, you know, a number of uh, sources from which you are kind of distantly connected. Um, yeah, your sources might just be bad, and there may have been insufficient validation done. Okay, so models must always be validated after they're created. That's the responsibility of the human to do, I suppose. Okay. Other issues when it comes to bias is just false information. So perhaps you choose a data source to build your model around that is full of things that just aren't true. Okay. Uh, Perhaps it relies too much on the kind of wisdom of crowds. And in this case, the good stuff hasn't necessarily bubbled to the top, so to speak. Okay, and then sometimes your data collection technique is just flawed. You introduce all kinds of sampling biases. Example here is estimating the average salary in the UK by looking at the salaries of people in London. Okay, uh, this won't be representative of the whole of the UK because in London salaries are on average higher because it's more expensive to live there, etc. This is an interesting one. The poor labeling of data. So if we have a group of cats and dogs, you might see this example used a lot because it's a really nice intuitive one, but we could label them as felines and canines or just both mammals or both four-legged creatures, pets. Like at some level you start to lose information or you leave room for something that isn't a cat or a dog to fit into the same category. Okay. And people have all different kinds of pets, so there's also an issue of poor aggregation. So let's say you have a 33-year-old. Um, categorized as being 30 to 35. Okay, that's reasonable. But then, as you can see, these ranges start to just make no sense. Uh, I want to kind of give an example of this. So, if we have 100 people who are all aged differently, maybe we could represent that as a list of random integers between 0 and 100. Okay, let's say I have 100 of them. Okay, so here's that. Just go to run it again. And then maybe I want a histogram of this data. Okay, this is what I get automatically. But there's an option in histogram to use a specific uh, bin width specification. So I could technically use a bin width specification of 100. Let me just, to be sure, let me use 101. Okay, all of the data is contained within here. Arguably, this is accurate. There's nothing necessarily wrong with this, but as you can see, it's completely useless. Um, yeah, so instead I might leave the automatic one or choose a different number of bins, like 20. Okay. Now this next section is a bit more kind of thinking about the societal impacts um, of bias, and we've used the title "Poisoned Data" here. So some of you who are familiar may know the story of the Microsoft chatbot called Tay that was essentially uploaded to Twitter. Um, I can't remember when. It's probably the Wikipedia at this link. I think in the 2000s. And it said that, well, the claim was that this will learn from conversations it's had with Twitter users and then start to come up with tweets of its own. Okay, this was essentially hijacked by, I don't know, malicious actors, let's say, that wanted to have some fun with it and essentially pollute the information that this chatbot was seeing. So in less than 24 hours, the chatbot was coming out with racist, misogynistic tweets, which I guess was not what Microsoft originally intended. And you can look up the story if you're interested. Uh, Now, as someone who understands this kind of thing, and as many of you in the audience, you can kind of brush this off as a bit of a funny old story where uh, the Microsoft team were a bit short-sighted. But if you think about how the general population might take an event like this, they might see it as the artificial intelligence took less than 24 hours to essentially become sentient and become evil, which has lots of ramifications for society if that's, people's view on artificial intelligence. Whereas if you understood the process, you just realized that there was a bias in what this chatbot was being trained on, okay, because of the presence of malicious actors. Okay. We have another example here where uh, in a slightly more, I guess, beneficial to you, you might be able to hack or hijack certain promotion algorithms where if you were to only use an account when it was offered a promotion, the algorithm might keep offering you promotions because it notices you only ever use shopping, or you only ever shop, for example, when you have a promotion, and you may end up essentially gaming the system. Okay. Now, that was a lot of me talking through the different types of biases, but here we've got a quite a concrete example. It's by no means a big data set, but it uh, tells you, well, it lays out the risks of a data set being unrepresentative. So let's assume a population has a 50-50 ratio of males to females. This is about right. But the data we sample has way more males than females in it. And this is the data. And what we do is sample their heights. So this is in meters. We have a female that's 1 meter 67, and so on. So let's store this as our data. And we're going to make a classifier using this function classify. So that took a fraction of a second to run, but what this has done, it's taken this data and it's built a classifier function in Wolfram Language. And now let's give the input 1.67. Okay. Looking at this and have a think what you think the output should be here. How should the classifier classify 1.67? So what it does is it predicts male. Now, this is because most of the data that has been seen is male. Therefore, even though we have an input that matches the only female input, because of the majority of the data was male, from a probability point of view, this classifier function will always guess male. We can have a look at this actually. So we can make a plot of the probability of this outcome. Let's say from 1.6 to 2 meters. Okay, and as you can see, it assigns constant value that's always going to be less than 50%, so it's never going to be selected because that's what this classifier function does. I think if we can just query the probabilities here. Just got to check the documentation actually. Okay, so with a 87.5% probability assigned to male, it's always going to just give us male. Okay, how do we get around this? We've clearly got an issue of a sampling bias, and we should rethink our sampling method in future. And we can correct this by using what's called class priors, where we're essentially informing the model that it should be a 50-50 split. To try something else. This has worked differently in the past, but yeah, in principle, you can see what the class priors is trying to do. You can read the documentation, but I think something is going wrong with this example. I'm not entirely sure, but when I tried this before, actually guessing 1.67 with those class priors does give you the female as the output. Okay, I'm gonna have a look into this. Okay, moving on. We also have human assumptions kind of folded in uh, to certain models. Uh, this perhaps requires us to really think deeply about how true something is, if it's tainted by some human assumptions. So yeah, always you always must think, when is something a proxy measurement for something else? Okay, if it's a proxy measurement for something else, it's not the truth. It's not that thing. It's some proxy for that thing. So the example we've got here is some historical controversy of the Pennsylvania Board of Probation that used uh, past reoffences to determine the risk of another reoffense of a criminal, of someone who'd been to prison. Okay, so this was their simple model. They wanted to see whether a released prisoner will reoffend. So they have someone is released, they either reoffend or they don't reoffend, and what they're trying to predict is, yeah, will a released prisoner be reconvicted? So that's a different word already. Reoffend is here because that's the thing they thought they were predicting, but what they can actually measure is whether they're reconvicted. Okay. Now, going on to the richer model here, we can see the problems with the initial oversimplified approach. So this is a bit more complicated. It's still rather simple. Just going to zoom out, but let's try and walk through it. So it's someone is released, they reoffend and they're convicted straight away. Okay, maybe they reoffend and they're caught and then they're convicted, but maybe they reoffend, they're caught, they're prosecuted, they're not convicted. Maybe they reoffend and they're just not caught. Okay, maybe they don't reoffend, but they're prosecuted and convicted. So all of these kind of paths through um, the tree, let's say, they could happen, and they're not what was being measured. So we can think about it in this way: we were muddling up uh, the notion of just reoffending here with one, the likelihood of being caught; two, the likelihood of being prosecuted if you're caught; and then three, the likelihood of being convicted when you're prosecuted. Okay, so this is a complicated issue. And then there's some interpretations of this here. So essentially, the accusation was that there was too much human bias injected into the model, and the human bias of the people on this parole board. Now, I don't know if this is true or not, but this is the accusation, and then this is the risk of oversimplified models. Okay. Now this is kind of linking to the histogram idea I had before. Someone can be estimated to be between 5'10" and 6'2", and they're actually 6 foot tall. This is an example of um, accurate data that has some uncertainty attached to it. Okay, this is not bias. And there's a statement here that with enough data, the true signal will emerge from the noise. Now, I want you to think about this for a second, because what it's really saying is that it's okay to have uncertainty associated with our data. And the problem of, okay, what's the percent accuracy you need to make kind of X% conclusions? That's a non-trivial problem. Now, my background is actually in astrophysics, and in one of my projects, I looked into this that if you can measure brightness deviations of, let's say, 5%, what accuracy on your measurements do you need in order to be able to do that? Okay, so you have a star that's at some baseline level of brightness, and then maybe you claim that you can measure 5% dimmer or 5% brighter. Okay, what is the accuracy on each data point you need to be able to make that conclusion? Now, an easy answer is that as long as it's less than 5%, maybe that's okay, but it's really a non-trivial problem, and statistics is hard, okay? Yeah, I like that I can have that example to kind of relate to when I'm thinking about um, the accuracy of data. And then here we have how biased data can still make good predictions. So if you have like consistent bias in like a model that's based on surveys, in this case, a model to predict salary based on age, and the data came from a survey. Maybe people who are taking that survey will self-declare a younger age. And then I think what this is getting at is that, let's say this model is complete and you go on to find out salary based on age. Maybe you self-declare as a younger age when you're using the model even. So those biases are consistent. I'm not sure about that example, but I think that's what it's trying to say. Okay, so we've seen one kind of male female classifier that didn't actually go the way I intended, but this is more of a story of of what happens when you try to essentially remove something from your data collection. Okay, and some of the ramifications of this. So we have this notion of protected and sensitive classes, legally protected by various, human rights laws in the EU, for example. So, for example, it's not allowed. It's not allowed to discriminate on the base of someone's gender. Okay, so the example that I'm going to use here is car insurance, which was more expensive for men than women. I think young men compared to young women, young men were paying more. Okay, because the car insurance companies were asking, "Are you are you a man or a woman?" Okay, now so happy with that. In December 2012, the EU made it illegal to discriminate on the basis of gender, but in the following years after 2012, the problem didn't go away. Okay, men were paying more for car insurance, and that discrepancy actually increased in some cases. So, what is going on there? And really, it's demonstrating that just because you remove the question of someone's whether someone is a man or a woman, you still have all of the signals kind of shining through that indicate, on average, whether someone is more likely to be a man or a woman. All right. So if I can click 2017 here, and it'll show us a tab of the kind of extreme case of what I'm referring to, right? So it's someone who, in the form that they're filling out. They say they're a scaffolder and they drive this much a year and they have a kind of muscle car versus someone who says they're a midwife and they only drive this much per year and they drive a pink car like this. I agree this is a kind of extreme case, but hopefully it shows how the what I mean by the kind of signal shining through. Okay. So yeah, the bias is still emerging if you have correlations between classes like job and type of car, that kind of thing. And this is where you get no-win situations. So uh, whoever's the decision maker in this case may just have to choose the type of bias they want to stick with. So they might just choose the bias that, I don't know, disadvantages the smallest number of people or keeps the insurance companies from losing out economically. You know, you can kind of imagine how these situations will go. Should a cohort have to kind of pay more for the, more reckless driving of another cohort, for example? It's a tough problem to solve. Okay, so now we can move on to validation. The way we're going to do this is to create our own classifier again, in this case, doing some image processing. So yeah, sometimes we have these black box devices, which are our machine learning models. Okay, we see inputs going in and we see inputs coming, we see outputs, but we don't really know how they're working. Now, it's based on our verification of the output that we can kind of um, decide whether to trust them or not. So here we go. We have this classifier, which is called dog or cat. It has only two training examples. All right. So it's made the classifier function. We're going to run that classifier function on the exact same image. We're going to get dog. And then for this one, we're obviously going to get cat. So think about what I've been saying this whole time. If we imagine this classifier function as a kind of model with weights that are parameters that have been optimized, okay, the the weights and biases in this model have been optimized for those two images only and no more. Okay, so this model is very much not generalizable, as we will see for this next example, where we run it on this black cat and we get dog. We run it on this image of a woman, which I think is a famous image processing example called Zelda, and it says that they're a cat. So I would hazard a guess that the thing that's similar between this and this that's making it say dog is the grass, because the computer doesn't, well, it doesn't essentially know what to extract because this image is brand new for it. Okay. So obviously, this is a terrible model and we can't generalize this. It's the unseen data that we need to use to validate our models to ensure that it's generalizable. Now, s- uh, I want to talk a bit about underfitting and overfitting here. So, an issue with underfitting, let's say I reduce this degree down to 1, is that we might miss some of the complexity of the data. Okay. So, maybe there's some kind of internal oscillation going on here. It's not entirely obvious from this data set, but perhaps we wouldn't want to use like the most basic of fits. All right, let's kind of up the degree a bit here and see what's going on. As we have a model with more and more parameters, the parameters here, I guess, are the coefficients of the polynomial. You can see that we are fitting the model closer and closer to the data. And let's just show this in the extreme case. Our model goes through every data point perfectly. Imagine the residuals are 0. Okay, is that a good thing? Well, instead of modeling the behavior of whatever's going on here, which we can pretty much say is something like this. Instead of modeling behavior, we've just modeled the data. Okay, the exact data that's in front of us. Um, yeah, so the residuals might be small, but the model will be terrible for data that's like even a tiny bit outside the range. And then maybe it will, maybe there's issues for data even within the range. So, for example, between this point and this point, the model says here, but in the overfitted case, it's somewhere off, off way up here. Okay, it's a very important notion in terms of models, underfitting and overfitting. Okay, now we can talk about how we measure the success of a model. So here we've got a neural net that's trained on MNIST data, so it's handwritten images. Okay, for example, here this is clearly 6, 3, and 5 that's been written down. How good is the model at identifying these handwritten images as numbers? So you can see it's done a good job with these 3. So I already loaded this beforehand. I'm just going to take a random sample. This is that input to output labeling I talked about earlier in supervised learning. So we're going to, and this is test data, by the way, I should say. This is contrary to the dog or cat example before. This neural net has never seen this data. Okay, so we can use it to validate the model. So let's see. We can use this built-in function called net measurements. And if we want the accuracy of its prediction of these test data set. Okay, so it's around 98% accurate, and we can make a confusion matrix. So on the diagonal here, that's where we've had correct identification. Okay, so the 0 was identified as a 0 974 times out of the 980 zeros that were in the data set. All right. This is only a random sample of 20 of M-test data here. And if I run the length on M-test data, I'd say we're going to get around 10,000. Huh. Yeah. Okay. Okay. So confusion matrix. It's very clear what the long diagonal or the main diagonal means. Now let's look for some other hotspots. So here we've got 16 where the actual class was 4 and the predicted class was 9. Okay, so you can imagine in your head, maybe sometimes the way you draw a 4 looks a bit like a 9. That's the issue here. It's interesting, though, that it's not necessarily symmetric. So not many 9s were predicted to be 4s, but I'd say 16 4s were predicted to be 9s. Okay, this confusion matrix is really useful for stuff like this. And you can see why the MNIST dataset is so infamously used when you're talking about these machine learning examples. Okay, we can have a look at the false positive rate and the false negative rate, which is pretty much just extracting data that's in this confusion matrix and converting them to probabilities. Okay, welcome back to the confusion matrix as well. All right, this is we're going to make a predictor function on some house prices in Boston. Okay, we've made sure to delineate between training data and testing data. So this is our test data here. Just going to show you Okay, so this is the form the data takes. It's actually like some properties of the house and then how expensive the house is. I'm not entirely sure what the properties are, but you can have a look in our data repository for this information. Okay. Just like the neural net repository before, we can access Wolfram's internal data repository. All right, so we're going to use predictor measurements to see how well the model performs on the test data. This is some measure of success, and then this is the comparison plot. So this is just a number. This is a bit more. This, I believe, is the root mean square error um, when you compare like the actual value to the predicted value. Okay, so here we are. You can see that it does a pretty good job. Because this is a prediction rather than a classification, we have a comparison plot. And this is the kind of predict version of the confusion matrix. Okay, we have what was the predicted value, what was the actual value. If everything lined up on this main diagonal, it would mean that we had perfect predictions for every single house price. Okay. But as you can see, these things are so easy to extract in Wolfram language. Okay, they've got intuitive names. Um, you could run machine learning models in seconds. Notice as well, I don't have to specify a method. So when I'm doing things like predict, there is an option of predict, which is method goes to something like decision tree or random forest. Okay. Uh, we'll jump to the examples in the documentation that use methods. So here we can specify the method we want. If we don't do this, then Wolfram language will perform some machine learning and actually automatically select the method that is performing the best. So it's kind of like training and validating itself as it goes. It's really, really impressive. All right. Okay, here we've got some issues of the longevity of models. So some data is not always fixed. Here we've got a contrast of chemical properties, which we would assume are fixed, versus people's fashion choices, brand names, things like this. These things change. And then we need to find the balance between updating the model regularly and or rarely. Okay, so if we update regularly, we won't have much data, but it will be up to date. And if we update rarely, we'll have lots of data, but this might be depreciated. It's also important to think about your model like in the context of um, like the actors involved of the things you're trying to predict. So if you had a model that could predict the stock market perfectly, then the uh, the stock market would adapt to the existence of this model, and then it would no longer be useful, if that makes sense. Okay, so this next section we have it's kind of exploring when you need to make decisions and when not being wrong is is better than being right. I think that's what it's trying to say. Yeah. So sometimes this is very important. And we've got a situation that's described to us here where we have a certain disease that is known to be incredibly fatal. Based on the output of a medical test that ranks someone from 0 to 5, a patient is diagnosed as healthy or diseased. But luckily for us, there is cheap, harmless drug that will instantly cure someone of the disease. All right. So here's the classifier: 0 and 1 are healthy, 2 is diseased, 3 is healthy, 4 is diseased, and 5 is diseased. Okay. Now let's see what 2.5 gives. Okay, it just says diseased. But think about the kind of the cost associated with a wrong prediction here. Okay. So if you incorrectly classify a diseased person as healthy, then they won't get the drug and you're almost guaranteeing their death. Okay. So we need to kind of update the model in some way to really discourage I- identifying diseased people as healthy. All right. So we can have a look at the probabilities of this. And the way we're going to do this is with a utility function. So let's have a look at this. Here, we've got when someone is healthy and they are predicted to be healthy, this is assigned the value of 1. When they're healthy and they're predicted to be diseased, um, it's 0. Because this is not too big of an issue, right? If you're healthy and you get diagnosed as diseased, then you just take this um, cheap, harmless drug that is assumed to not have any adverse effects on healthy people, and you're okay. The real issue is when someone is diseased and they are predicted to be healthy. That's why we use -1 here in the utility function. Okay, so we can look at this again, and we can see that the outcome is still diseased, but maybe we can kind of, in the first case, see an example that would be diagnosed as healthy. Uh, okay, okay, here it's still healthy, but if we really increase the penalty here, let's see what happens. Okay. So if I've kind of 10x'd the penalty there assigned to a false prediction, then the model will err on the side of caution and always just predict diseased. Okay, so it's a real balancing act to play off here, and I've just, you know I've played around with a very contrived example, but hopefully you get the idea of what the utility function is trying to do. We need to add a penalty for false negatives. Okay. And we can also plot this ROC curve, which stands for the receiver operating characteristics. So we do is we get the data from the uh, handwritten digits identifier. Let's have a look at this. Let's just take 10 of the points. Let me just have a look at the structure of points a second. Okay, had a slightly different structure than I was expecting. Okay, so I believe these are examples of the false positive rate. So what this plot is showing, and this is quite high level. I'd encourage you to check this out. The graph shows us how well a binary classifier performs at different threshold values. Okay, so we can like vary the threshold at which we say something is a 7 in this handwritten digit example. Okay, we have the recall on the y-axis here and the false positive rate on the x-axis. Okay, we've actually extracted the points from this using net measurements and then use a list line plot, but we can actually do it directly on the net measurements using this ROC curve plot argument. And as you can see, this looks very different because the x-axis extends from 0 to 1, whereas here it's just from 0 to 0.08. And I believe a perfect model for this ROC curve would, I think it would follow this exactly. So here we have some information on the ROC curve. You can look into how it's, actually defined. Okay. Okay. And to make sure I get onto the final section on explainability. So this is a slide on just the human weaknesses and strengths when you compare them to the computer that's making these data-driven decisions. Humans can let emotion get in the way of the decisions. They have their own biases. They sometimes don't react as quickly or can't compute as quickly as computers, and we also have the issue of fatigue. Now, human strengths sometimes actually lie in their biases, and most importantly, here is the kind of adaptability of a human to the situation in which they find themselves. So this slide is all about the difference between when we want a prediction and when we want kind of control of an outcome. So if we just want to be able to predict something, correlation is fine. Okay, when we have the clear relationship between two uh, variables, then we should be able to predict one or the other quite well. So let's say this is our observation that we can predict B quite well if we have A. One explanation might be that A causes B. Another might be that B causes A, and we just happen to measure A first. However, explanation three is that we have this confounder that causes both A and B, and it makes it look like there's a relationship between A and B. Okay? So this is a very important concept in causal uh, inference and that whole study. Okay, here's an example where we've got someone who is bearded. Perhaps you can predict are in more car crashes, and we've got a quite an obvious confounder here that the property of being male is the actual confounder, and this setup makes more sense than this one. Okay, and sometimes the way you can kind of extract some like causal link is just by performing like the controlled experiments uh, over and over. Okay, so that you can have more confidence in the causal links that you identify. Okay, uh, this last section we're going to look at sensitivity analysis, and there's just an aside here which kind of links to the thing I've been talking about this whole time about if you wanted to identify a table, a human might identify it with its four legs, flat surface, etc. But for a machine, a picture of a table is just, you know, a cluster of pixels with various RGB color values. Okay, so the features it extracts, we should not expect to be the same as humans. And again, I know I've said this before, but feature space plot is really powerful in this regard. So we can even give it some images and it can kind of separate those in a feature space. Oh, this is cool. This is using our new tabular functionality uh, to organize flags or the image of a flag in feature space. Mm. Tabular is new in uh, 14.2, by the way, for those who are curious. I think it's going to be very powerful. Powerful way to deal with rectangular data. Okay, so the sensitivity analysis is going to center around wine quality. So we have this example data set in our resource system, which assigns a wine quality value given all of these properties, right? We have our predictor function that I defined earlier, and we have this test example. This data represents a wine, and we've used our predictor function on this data to predict the wine quality. Okay, we can also look at the estimated accuracy of the prediction, which takes the form of a normal distribution centered around this mean of just above 7. Okay, we can also extract the SHAP values. So let's extract them first, and then we can talk about them. So as you can see, for each of these variables, fixed acidity, volatile acidity, alcohol content, we have a corresponding what's called a SHAP value. And this is named after someone called Shapley. You can think of these as pushing the prediction one way or the other, causing it to go up or down, and also depending on whether it's positive or negative, and also pushing the prediction one way or another with different strengths. Okay. So looking at this, the alcohol quality seems to push the prediction to higher and higher values. So higher and higher values in this case is a higher wine quality. So it looks like alcohol content is actually very important when it comes to wine quality. And a very important feature here is that the values, the SHAP values, add up to the difference between the prediction and the average quality value. Okay. So adding all of these up. And as you can see, we could just use total on this dataset object, which is quite nice. And then here are some visualizations that I made before where we can actually have a cumulative impact plot of every feature on the result. And this has actually ranked them such that we get the biggest kind of push to the right from alcohol. And actually only one of them was negative here. You can see a slight kind of pushback to lower number, which this is volatile acidity. Huh. Oh no. No, it must be this free sulfur dioxide, which was in fact slightly negative. So this is doing the kind of pushing back down to lower qualities. And this is an example of the accumulative feature impact plot of the whole wine quality data set. So it gives us a really nice visualization, I think. And we can also visualize the SHAP values in this way as um, a feature impact plot that can be smooth or contain the points. So you can see where there's like humps in the smoothed, that's where we have an increased density of points. And then these are the SHAP plots of the entire data set again. So lots of sensitivity analyses we can do using all of these built-in functions, and there's just so many of these that are very well documented, um, and there's no reason why you can't use these on your own data. This is a ICE plot, so a individual conditional exploration, no, expectation. So this takes each instance in the data set and visualizes the dependence on this property. So in this case, sulfates. But I could just as easily pick pH. Okay. Okay, so we're coming to the end now. This slide is it's essentially talking about some of the responsibilities you have when working with big data and these machine learning models. Is that you need to be very explicit about your collection methods, the sources of training data you pick, your assumptions, the architecture of your model, and the data you use to validate. Okay, so there are lots of choices that are going in here. If you want anyone to be able to reproduce your work or critique your work, you need to be clear about these choices. Okay, there's also lots of gray area when it comes to the ethical issues behind, you know, data brokers and um, kind of consent behind data collection, that kind of thing. So the GDPR actually requires informed permission for use of data. And this corresponds to whenever you do a kind of web scrape, there's an implicit kind of informed permission use of that data, even if it doesn't seem like it. And this also talks about how when a model is overfitted, there might be a small data set, then the model may be able to predict real values that correspond to real people and their data that's technically private. Okay, and I'm sure some of you watching will have heard of kind of prediction algorithms being able to predict people's actions almost better than they know themselves. You know, when it comes to um, the types of products people buy and that kind of thing. So these are some ethical issues we have to be aware of, and also aware of the responsibility that we have compared to that of the computer. Okay, so thank you for listening, everyone. I'm just going to look through the questions I have, but if you want to send in a question, now is a good time. So Simon asked, is the dimension reduction done by PCA, which refers to principal component analysis? So this is a comment on the feature space plot type of thing I was talking about earlier. Yeah, when I was talking about these like word vectors. So really good question. It very much could be. So we have this function principal components, which just calculates the principal components, performs your principal component analysis. We also have, and perhaps this is more general, dimension reduction. So let's look at the documentation here. We can use this dimension reduce function to essentially pick the number of dimensions we want and then also choose a method. So TSNE is a common method. Uh, autoencoder, I believe one of the methods is in fact principal components. So yes, so we can do more general dimension reduction. Okay. EL has said, not a question, but it would be great to see a webinar about causal inference in the future. Okay, that's good to hear because I have a colleague who has essentially built some causal inference functionality, the directed acyclic graphs, that kind of thing. And he actually did a Wolfram Technology conference talk about this. So I'm sure we can get this to you somehow. John asks, does reinforcement learning help to move the ML model towards more useful, i.e., less noise features of the data? Hmm. I suppose so. I don't, I think there's probably lots of ways reinforcement learning could happen. Um, yes, if you can think of the model as spending too much time combing through the noise being something you'd want to discourage and focusing on the um, useful features, something you want to encourage, and in a way, you're kind of you're doing reinforcement learning around that. So I suppose so. I'm not an expert on this though. I'll just address some questions from YouTube. Someone says another way to have no bias is to just have all the data, as well as something having no bias being random noise. I suppose you could also have all the data. So that's correct.